Good morning. Good morning, BGSS. Okay, today is Friday, the 17th of August, 2018. This is the nybbles.io daily programming stream. My name is Jeff. I write code every day, and I stream here on Twitch Monday through Friday. Hey, Flathead Screwdriver. I just have to ask, is your cousin Phillips head screwdriver? Sorry. It just popped into my head. I am working on a project called Basecode, which is a new programming language that I am designing. I'm working specifically on the Bootstrap compiler, which is written in C++. In the lower left of the screen, you'll see the work that I have to do. And yesterday, after the stream, I eventually made some fairly good progress. So I tidied up some remaining areas where things were being passed that didn't need to be passed. I made some things I had as pointers. I made them references just to be consistent. So program is officially deflated. So yeah, program is like any other element now. We still have an on emit, right? Program is still kind of responsible right now for driving the compilation process, which is fine. I don't really see that changing, although I think this method, right, needs to be, I need to break this up. I need to refactor it. I'm not going to do that now, but it's, we definitely need to tidy some of it up and make it more reusable, especially like this area here where we're handling like what it means to be a variable and how that gets emitted. I think a lot of this can get converted into a function that can be reused in a couple different places eventually. But yeah, program is 315 lines now, much smaller, and he's like every other element. And in that vein, what I did was I took all of the non-element classes that were in the elements folder and I moved them up to the compiler root. So the AST evaluator, the element builder, the element map, the scope manager, they all live here now because they're really, all of these things combined kind of are what make up the compiler. And so I'm going to try to keep the, elements folder kind of dedicated to just actual elements, and any other kind of machinery would go in here. The other thing that I need to do is, although again, I'm not going to do that today because I think it'll be a slightly painful refactoring, but I need to make the alpha core library, I need to just tidy it up a little bit from the perspective of using it from the outside. What I would like to be able to do in the, like for example, in the compiler command line program, I'm including all these separate pieces, right? But really what I would like is pound include, alpha core or alpha whatever / compiler.h or something, right? And I have a public include folder that has a nice public facing include that handles including all the subparts. And in order to do that cleanly, I want to hoist some of these things like this. Typically, when I do libraries and things, I have like this header file that I'll either call types or I'll call it whatever I think the name of the library is, _types, because it's like all the forward declaration and all that stuff. But I have that in a couple different spots right now, and I need to clean that up. So I want to move, either create a new one, right, that includes some of these others, or move compiler types up to the very root and refactor it, and then add a public include folder here in the library, excuse me, that then includes all the private stuff. And that way, theoretically, in our CMake file, I could set up an include target, or an install target that would copy this stuff to user local or whatever. And what would be in the include folder would be like a base code. So it'd be like include, base code, that top level include, or a couple top level includes, private, and then, or these folders, right? These would just be like the private folders underneath that, which is a common pattern. Again, not a huge priority, but it did kind of pop into my head yesterday as I was refactoring. And I thought, okay, well, that's not too difficult to do. So let's see, alpha core, add public include folder, and refactor forward decal covers. Put that out there so I don't forget about it. Now we'll move that down here. This is not super duper important. Hey, Mr. Sahin, I'm doing good. Okay, and then, so program is all nice and tidied up. Then in AST Evaluator, I also I added add assignment. Yep. So one of the issues I had, one of the tasks I had, was to refactor assignments so that I didn't have so much code duplication, and I think I succeeded as a first pass. So I created this add assignments to scope, and this is the block of code that used to be in the assignment case for the AST translator. Now you can see how nicely this shrunk up. Now I just make a list, I call add assignments to scope, and much nicer. Also, add composite type fields. This shrunk up a lot too, right? Because now for assignment, I can just call add assignments to scope. If that succeeded, I can create my field. And there were actually two cases. So add assignments to scope ends up calling add identifier to scope in a very particular way. Here we have a case where there's no assignment, but we're declaring something. So I created a common helper function called declare identifier, which is used in a couple spots. And this handles the simplified scenario of calling add identifier to scope in the context of an unassigned declaration. There was one special case that I tried to refactor, but ended up backing it out and just leaving it the way that it is, because it's a very special case here. This is inside of a statement where the statement is just a symbol with a type. So that's a special kind of declaration. It's a couple lines of code, so I'm not too worried about that one. So let's see. So Meshuggah Sahin says, is it air conditioning? I'm not sure what you mean there. Nizo says, do you have any tips for a software engineering student migrating the dev environment from Windows to Mac OS? Anything in particular to check out, or is it more or less the same? I mean, it's not the same. Yeah, that's a complex topic because there's lots that you probably would want to look at for OS 10, but it also depends on what's your development stack, right? So I don't know what tools you're using. So some of it's going to depend. Also, I don't know what your budget is. The other thing that you should be prepared for with OS 10 is that in general, in the Apple space, be prepared to pay for stuff, I guess is really what I would say. Yes, there's open source, but the Mac community, the Apple community in general, has always been more willing and I guess conditioned, if you want to look at it cynically, to pay for things versus the Microsoft space. So you're going to find a lot of little tools that you're going to want to have for your Mac, software tools, that you have to pay for them. I mean, there's just, unless you want to be a pirate, then you're probably going to have to pay for them. So I was also able to refactor proc expression. Again, this shrunk up pretty nicely. It's now much more just some boilerplate calling a shared function and just handling that after the fact. So those, after doing all the structural refactoring, getting all that stuff cleaned up, I changed directive. Directive was taking both a session and a program pointer. They just take a session now because program's on there. There are lots of other little things where I was passing stuff around that I didn't need to, so I tidied that stuff up. But all in all, that whole cleanup refactoring's done. I'm very happy with how that turned out. Last night, I decided, what the heck, I'll spend an hour and see if I can put together the transmute operator. So what I ended up with for transmute is actually pretty simple. So we grab the target register, because there would be a target register for this, because transmute's always going to be on the right hand side of an expression. We grab our current instruction block from the assembler. Given the expression that's inside of the transmute, right? So we have, let me bring up the example. So we have transmute, the type that we're targeting, and then this is expression, whatever's inside here. So we use this register for helper, which is on element, and we pass in the session, we pass in the element that we're trying to determine, hey, is there a register for this? Now it turns out this is referring to a variable. So because it's referring to a variable, then this temp register is actually going to be representative of a variable, an assembler variable that we have in the emit context. So we take this temp reg, we push it, and then we emit whatever that internal expression is. In this case, it's just would be dereferencing the identifier, so that's going to load the value of that identifier. This is going to do a read, essentially, on the variable, which is going to produce potentially a couple of setups for registers, right? It's going to load an address register if it needs to, and then it's going to do a load from that address register to our target. We get rid of our target register because we're done there. And then transmute is actually super easy because it's just a move. It's a move from one register to another given the size of the target register. So we know that we're moving to a, U8, right? In this case. So target register is going to be sized properly, and yeah, and then we just take whatever the temp register was for the value that is inside the expression. So if what's inside the expression is a word, we're going to load, and we're trying to transmute it to a byte. That means we're going to take the bottom 8 bits, right? And we're just going to move them into that value and store it. We're not going to do any other kind of translation to it. And so in this case, because it's going to be a move.b, or if we had a 32-bit value, move.w, and we're only getting the bottom 16 bits, we're copying those lower bits into the target and storing that in memory. And then I create a comment so that we can see that the move instruction is actually the transmute. That's the intention of it. So we'll run this and we'll look at the transmute. If you want to subscribe to the channel, I believe you have to do that through the Twitch user interface. I don't know. Also, I think Twitch commands are /. They're not bang. Nightbot is the exclamation point. Okay, so here's an example of what transmute ends up becoming. So, so we load the address. Let's look at our example. So we create our target variable, which is a byte. We're loading 3, so 3 is up here. So then if we look at the output up here, we're getting the address of the 3 variable and putting that in I2. We load the value of that variable and we put it in I3. Now it happens that I'm casting that as well. We can just ignore this. We're going to actually make changes here. But I3 still has the value from the variable 3. So then we fall through to our transmute. We get the address of our target transmutation magic variable. Then we do the transmute itself, which is just a move in this case. So I3 is a word. It's a 16-bit value. So we're moving the bottom 8 bits of that to I1. And then we're storing whatever's in I1 at that variable location. So that's transmute. Very easy. Ended up working quite nicely. So cast is very similar. And I went through and I pulled together some rules on what should actually happen here. So for numeric casts, which are going to be the majority of them, if we're casting between two integers in the same size, it's a no-op. If we're casting from a larger to a smaller, it'll truncate. This will be essentially the same as transmute, more or less. Casting from a smaller to larger will widen. It'll zero extend if the source is unsigned, or sign extend if it's signed. Casting from a float to an integer will round towards, will floor, essentially. I'm not sure what to do about nan or infinity here. I'm guessing that those will just produce zeros, but yeah, I gotta think about that. Casting from an integer to a float will make a float, and so F32 to F64, that's essentially just a reassignment, more or less. You could almost view this as almost kind of like a form of extension in a way, but it's lossless, right? F64 to F32 will try to produce the closest possible value and round if it needs to. Casting a bool to an integer type will yield 1 or 0. And then casting any integer type whose least significant bit is set will yield true, otherwise false. And so for numeric types, that's pretty much it. Pointers, we will need eventually pointer casts. And these are really just numbers. It's numeric to pointer. And most other casts are invalid. So right now, this is doing the same thing that transmute's doing. It's essentially the truncate case, but that's just one of many. So we need to add code in here to support the full range. Before I do that though, I'm kind of noticing sounds like my microphone is peaking. I think sometimes I accidentally bump this thing. Hopefully that's a bit better. Okay. Okay, so what we need to do, we know we're going to get the type from the expression, because on the cast, we have the type for what we want to convert it to, which that type has to match whatever the left-hand side is. So this is what we're going to be casting from. This is the source type. So actually, let's call that source type. And type is the target type. So if source type number class is equal to none, okay, so if our source type is not a number type, which is going to be true for all of these casts, that includes things we're casting to an integer, right? Because the pointer casts are just going to be like, I have this integer address and I want to cast that to this kind of pointer. That's what it's going to allow. But any other types right now, that's not valid. So let's test that. So we're going to create a string, and I guess I'll be explicit like this. And then I'm going to create a U32. And then I'm going to try to cast name. That should give us the error that because name is not a valid number type. So it can't participate as a source in a cast. I am building a language called Basecode, and specifically I am working on the Bootstrap compiler, which is written in C++. Once the Bootstrap compiler is sufficiently advanced, then I will move on to rewriting the compiler in Basecode itself. Putting the wrong one there. It's got to be source type. There you go. Now I probably should use the location of expression. So that's going to be clearer. This compiler, you asked about the use case for Basecode. Basecode is me experimenting with the idea of metaprogramming, and this compiler, yeah, there we go, perfect. So it's saying, hey, the type of this is string. We can't cast. Let's just say cast from. This compiler works a bit differently than other compilers. Because the compiler will run code during the compilation process. It has to have it in an intermediate format that it can run it in, but at the same time change it. So the compiler compiles to a bytecode, which is run by an interpreter built into the compiler. And then once the program completes the compilation cycle, that bytecode, which is what I'm looking at here on the in the output, will be translated, cross-translated to whatever native target you want. So the final output of this compiler is actual machine code for an actual CPU. The compiler is going to be designed from the start to be a cross-compiler. So you could say that you want an output for x86-64, for ARM, for Atmel, whatever targets we support, and the compiler will generate all those outputs at once for you at the end. Right now, though, I'm working on kind of the core of the compiler, so everything I'm doing is for the bytecode that the compiler uses internally. The bytecode's not intended, though, to really be run outside of the compiler itself. Okay, so that error works. And so alternatively, if we tell the compiler hey, I want to cast to this other type, so this is a valid source type. This is an invalid target type. Ooh. That's not good. And I think I know. No, maybe not. So for that particular case, we should be falling into this block. Different one. Okay, good. So this is correct. Because the right-hand side of this, the initializer, is not it's not constant. So we actually have to make a real assignment. Okay, so we're getting an assignment. All right, so here's our cast. Source type is oh, right, this is no, that doesn't seem right. Oh, or it's that one. Yeah. Okay, this is a cast to the byte, the U8. Yeah. We're not even getting to the other one. Because, right, that's part of assignment. So that would be binary operator. So we're getting, yeah, we're getting here on that second one. So what is left-hand side? Okay, not that one. There. Here's name. And there is a type, which is a struct type. String. Okay. Okay. So why is that one not being created? I think that's in program. So for string literals, we allocate variables. That's, okay. Here's identifiers. That's why. Uh-huh. Which is kind of wrong because why am I conditioning it on whether or not it has an initializer? Doesn't seem right. So I'm grabbing all the identifiers. Looping over the identifiers, casting it, checking the type. If it's a namespace or we don't have a type, we continue. Technically, at this point, if it's null, that should be an error. But if we find a variable that's in a procedure or is part of a structure or a names, no, actually it's part of a structure. Don't worry about those. These, because we're just trying to do globals. So if it's Boolean or numeric, yeah, I don't know why it is conditioning that. It should just be, if it's constant, if it's not, it goes in data. Okay. In the following examples, void names, I don't know what names is. He didn't declare it. Void dereference names, void address of names, which ones am I passing to the parameter by value versus by reference? I would have to see, so first off, I would have to see the prototype for my function. Without knowing what that looks like, I can't tell you. I think dereferencing names was the same as, I'd have to see what the prototype is to understand what that function is expecting. Knowing what the differences are between passing into a function as variable, address of variable, dereference, a pointer to variable, where? Are you saying that's like how you're calling it, or that's how it's declared? Yeah, I mean, like, you would have to give me an example of a function prototype, and then I could explain to you how you would potentially call that. I might actually be falling in here somewhere. Yep, I sure am. Return types. Yeah. All right, here's what I'm gonna do. Okay, so we get the variable. If it's within a procedure, we're not worrying about it here. If it's a part of a field, we're not worrying about it here. Otherwise, we try to grab the type. If it's null, that's an error. If the type is a namespace, then we're not going to do anything here. We don't do any variable declaration for namespaces. Yay, okay. Okay, so cannot cast to type U32. I thought, oh no, I know what I did wrong. In cast, I probably should fix that. It's not, it's the symbol that has the location. It helps if I can spell it. Is this, because we can't cast, but it's saying U32. Yeah, this should be the type we're trying to cast to, and this should be the location of that type. I think I might just have to fix the location on it. There we go. All right, I just gotta fix the location. symbol should have location on it. This seems reasonable. Yeah, that seems reasonable to me. Okay, I think that's the issue. Yeah, so in this case, we're looking up the type. We don't actually make a copy of the type or wrap it in anything. But because of that, we don't have, we have it at parse time, right? At conversion time, because we have the AST node. So we can show the correct location for that in the brackets for that type here, because we still have the AST node. But once it's been converted into an element, we're just reusing the type. So the way we fix that, is we just track that location, especially on the cast. I need to do the same thing on transmute. But we'll test it here. There we go. Okay, so I want to do the same thing for transmute. So for transmute, I think the logic here is kind of the same. If the type of the source expression is not numeric, then we can't cast from that type. If the target type is not numeric, then we can't transmute. Right, because this is very low level. This is aliasing bits, essentially. Right, so then in the evaluator, we need to look at transmute. All right. So I'll comment this out quickly. If I try to transmute to a string, that should give us the same error that we can't transmute to a string. Oh, right. Perfect. All right. And this should compile without any errors. Which it does. All right, I got to take a really short break, get some more coffee, be right back. Okay. Checking my email here for a second. Okay. All right, so cast and transmute now are checking their parameters. We can cast to a number. We can cast from a number. We can't cast from or to anything else. Because what does that even mean? So then, if we fall through here, we know that we have both the source and the destination type are numeric. So then we need to determine what combination they are. So if source type, I can't, number class is integer and type so if we're doing integer to integer, otherwise if okay. So if the source type is the thing inside the parentheses, is an integer, and the target type, that's what's inside the brackets. If those are both integers, then we're dealing with the integer to integer case, which are these. If they're both floating point, then we're dealing with these. Otherwise, we're dealing with and I'm going to cheat. Yeah, we already say that Booleans are an integer class, so that's perfect. That's what we want to do. All right. So either they're both integers, they're both floats, or it's an integer and a float. So if they're both integers, then we have what? We have, they're the same size. So if source type size in bytes is equal to type size in bytes, then it's a no op. And I'm actually going to emit a no op in that case, because then we'll get the comment on the no op, and we'll know the cast resulted in no instruction. When this gets translated to actual machine code, we'll strip these out. But inside the interpreter, it could be helpful to be able to see have a little bit of diagnostic information about what decision was made. So if they're the same size, then it's a no op. Although, I just thought of that. It is a no op, but so if it's the same size or size in bytes from the source is greater, in other words, if we're the equal or we're going to a smaller type, then we'll do this truncation thing. Otherwise, we have to do the 0 or sign extend, depending on whether or not they're unsigned, or if the source is unsigned. So if source type is signed, oh no. Look at my sample. So I'm actually going to fall into this case because the source is larger than the target here. So we should end up with a move that's a truncate. Yeah. So we're truncating from a word to a byte. That's correct. But if we do 4, and we say he's an S16, okay? Then we'll say 4 is equal to cast S16 3. Right, because this is a U16. We shouldn't, first, let me just verify, we shouldn't be able to just assign that. Did it let it? I think it let it. Did I say that was okay though? I think the type checker accepts that because they're the same size. Yeah. But this should also work. It should just yield the no-op case I handled in the assignment because I say, okay, if it's an S16 and a U16, they're the same. There's really nothing special that has to happen there. Yeah, so so I3 is the 16-bit value of 3, the variable 3, which is 128. We're going to store a byte version into 1, which is correct. So that's a truncate. Then we're just going to copy it, essentially. This is a no-op. Yeah, so see, we could do the no-op. The way we would do it is... I don't like that. We'll leave it this way for now. What I was going to say is I could change the target register here to just be the value. So it just essentially flows through. But yeah, I'm not going to, that's an optimization. Technically that's correct, right? There's no truncation going on there. We're just copying one to the other and storing it. Okay, so that covers those scenarios. Okay, so if the source is signed, casting from smaller to larger, we're going to sign extend. Which I don't have a sign extend instruction. So 0 extend. I'm kind of curious. So let me. Let's make this that, and then we're going to go to a larger type. So this is smaller to larger, unsigned. So this would be a 0 extend, which I think is, yeah, I think that one move will work, but I just want to see what code it generates, see if that's right, and then we just have to do the sign extend case. So we'll need either a move instruction with a sign extend or a separate sign extend instruction. Okay, so getting the address of destination, getting the address of source, loading the byte from source into I5, moving, yeah, so this would automatically be 0 extended here. Because we're only going to be, is that true? I don't know if that's true. It would be true if I clear the register. It would not be true. All right, yeah, I think we probably need an explicit. Because this is only a byte, right? We only changed the lower 8 bits of this register. So if this register had previously been used, the upper 48 bits would be whatever they were previously. So then we're interpreting the lower 16 bits here. So yeah, this is not explicitly making sure that that's. So really here in this case, yeah, this should have we should have something like move Z or. Yeah. Thinking like move Z, move X, right? Move Z is going to be 0 extend. Move X is going to be sign extend, or move S for sign extend. Okay. Sir Rackley says, hey, what are you hoping to achieve with the new programming language, or is it purely a learning tool for yourself? It's such a difficult question to answer. I'm doing this entirely for myself. I don't expect anyone else to ever use this. I've explained numerous times. It's not even that it's for fun, right? I'm doing this primarily because I want it. I don't care if anybody else wants it. I don't care if anybody else ever uses it. I don't have any grand designs. I'm not trying to make this the next popular anything. My expectations are that people will shit all over it and no one will use it. So, but I'm building it for myself. I'm going to use it. If I'm the only one that ever does use it, then I guess I'll be happy with that because I'm going to get benefit out of it regardless. I'm just trying to think if... I'm wondering if I want it in the move. Yeah, I think I want it to move, not in the load. So the way that a move Z would work is we would first set this, whatever the size is of the target, to 0. Then we would assign whatever the value of that register is. For assign extend, we would take we would 0, then we would take this, interpret it as a 2's complement, shift over the sign to that size, and then assign it. So we'd rescale this. Okay. Hey, Kubisis. That's not right. That's why I was wondering, I was debating on it should be part of the load. Or somehow, I mean, ideally, what would happen here if we were going, this problem is we don't know. Yeah, because what would be the easiest in this particular circumstance would be, which I think we could do, because this is where the load's coming from. Right? We're emitting, this part is part of the cast. That's this expression here. So we could emit a, we know what this target register is, this I5, right? So we could clear it. We'd have to clear it based on the size of the target register. So what that would do, we wouldn't need a separate instruction for zero extend, because yeah, really, we don't, our registers are not, our registers are not typed, the mnemonics are. See, unlike other architectures, on physical architectures, oftentimes the registers themselves are typed. Or if they're all 32-bit or they're all 64-bit, then they have these fixed rules of like, they don't do zone loading like I'm doing here, loading and storing and stuff. Instead, they just say, if you move a register into a register, then things just get cleared. So then you're always resetting state. So we have no op, we have truncate, we have sign extend, zero extend, float, extend, float, truncate. I think those are our cases. So if they're equal, and I'm keeping these as separate cases here, even though I'm doing the same thing, because at some point I can probably optimize that to be a no-op. But for now, they'll just truncate to the same size. This last one is, okay, they weren't both integer, they weren't both floating point. So then in this case, the source is the integer and the target is float. Integer to float. In this case, it's float to integer. And I'm realizing I don't need anything special for bool because bool just falls under the integer case, and it's a boolean's always a byte internally represented, so that's just going to be either a truncate or a zero extend, probably. All right, so now we have some flags. So we can say if mode is cast mode t integer zero extend, just as a test case. And then here we can have switch mode Okay, so before we emit the read or whatever expression is going to happen on the right-hand side, we're going to zero out in both cases for a sign and a zero extend. We're going to want to zero the bits so the destination register is going to be temp reg. However, because the size of the temporary register is not the size of the target necessarily. In this case, we want to make sure we clear it to the size of the target. So we're going to make a temporary register here that has the size of the target but the number of the temp, and then we're going to load that size with 0. Okay, let's see what that looks like. There we go. Oh shit, it's happening in the wrong order though. Why is it happening in that order? I bet I know why. Yeah, it's this. I need to do this right there instead of after. Crap, but I don't have temp reg. Oh, I love it. I love it. I love it. Crap. Yeah. So, you know what that means. Nisa, so I'm looking at your code here, and okay, so this code isn't. So when I said, okay, I think this is good. I mean, it gives me an example of what you're trying to do. But just so you're aware, in C and C++, the term function prototype means void my special func int long float char star. That's what's known as a function prototype. That's what tells the compiler ahead of time, without a body, that whenever you see this function name, this is what it looks like. This is what the parameters and return types are. So, with that said, in your example, you do have a function prototype for print. It takes a contact list, which is a class, I think. Although, okay, yeah, contact list is a class. Okay, so the way that your function prototype is written, you have void print contact list. Okay, that is a function that returns nothing and takes a copy of a value of contact list. That is the only thing that it can take in that situation, okay? So now, this gets a little interesting because in C, this would be really bad, okay? Because the C compiler is limited in how much it can optimize values like this for return types and for parameters. The C++ compiler can do some tricky things behind your back, according to the specification, to make this not so inefficient, meaning that behind the scenes, the compiler might actually be passing a reference to this. However, that's a detail. Don't get caught up in that. It's possible, but you still probably wouldn't want to pass it by reference or pass it by pointer here. You wouldn't want to be passing the whole value because that's going to get expensive. You're going to end up with copies, right? Which is not what you want. It's not going to behave the way you expect. So in your code, in main, at line 215, that is the only valid call you are making to print. Methods B, C, and D are not valid according to what you've written. You can't even use them. If you wanted to do method B, you would define print to look like this. If you wanted to do method C, well, so method C technically is method A, except that the way that you would instantiate your contact list, either you would have taken the address of that and then dereferenced it, or you would have allocated it on the heap and gotten a pointer and then you dereferenced it using the prototype you have already because you're passing by value. And method D just doesn't like, that's only valid if you had what I already typed, print contract list pointer, or if you had void print contract list, that would be also valid. You're passing a pointer in that case. Technically, you know, the pointer version and the array version in C and C++ are essentially the same. They can be aliased to be the same thing. So, well, so names are as a pointer. Well, okay. Yeah, I mean, yeah, these are basics, right? So like I would really suggest you probably should go back and read through or take just a standard C or C++ tutorial or something that talks about types. This is just basic type stuff. So again, in C++, the ampersand can be address of, or it could be reference. So there are two contexts there. Reference technically is related to a left-hand side declaration, and an address would be a right-hand side var value in C or C++ speak. So you would have references if the ampersand is L value, and address if it's R value. But I think where you're kind of getting confused a little bit, if I were just generally abstract this, you need to make clear in your mind the distinction between the thing you're calling and where you're calling it from, and how the way in which you call it can vary depending on your own, you know, you can make choices of how you want to deal with that based on the call context. And then there's the prototype of the function. That's what it is, right? That is what it is, and it doesn't change. So, but at the call site, right, you maybe are dereferencing a pointer. You maybe are taking the address of something. That's dependent on the call site. So there's two concepts there. And you need to keep those concepts straight. I got to change my camera battery. Be right back. Huge and all. Sure, shoot. Yeah, how am I going to do this? So I either need to extend the register for function, and I need to pass in extra information like hey, when you do a read, I want you to, zero out the target register for this size. To do it that way. Or, I don't know, I gotta think about that. What's the design purpose of having unsigned and signed integer in MIPS assembly? Well, it's not just MIPS. It's most CPUs, with the exception of maybe some really old ones and a lot of older IBM CPUs. Well, first off, there is no such thing as a negative number, right? Negative numbers are a scheme, just like there's no such thing as a floating point number. I mean, there's no such thing as a decimal number. It's a scheme that is something that is designed on top of bits to make those bits behave as if they have extra behavior around them. Okay, so I would say most modern CPUs use two's complement arithmetic. If you're not familiar with what that means, then you need to look that up. But the short of it is that negative numbers are a pattern that appears in the register or the memory location, and because it's still a positive number. In fact, negative numbers are very large positive numbers, literally. But it's only because there are special instructions in the CPU that understand two's complement that you actually get something that appears to act as if it's a negative integer value. So that's why. That's why there are two different kinds of instructions. And if you didn't have two different sets, then you would have quite a bit. You'd either have to handle all the two's complement on your own, right? Or the CPU just doesn't. Yeah, you would just have to do it all on your own, right? Which you could do, which is what I do, like in my interpreter. I handle the two's complement stuff myself because I'm, C and C++ kind of tries to abstract that from you. So, but anyway, yeah, that's why. Well, they don't, right? They don't exist as far as the CPU is concerned. I mean, as far as binary is concerned, there is negative is a flag. It's a bit that gets set. And if that bit is set, then it's negative. If it isn't, then it isn't. And in accounting, there are no negative numbers because double bookkeeping, which is centuries old at this point, found that people can't do subtraction in their head or in general. Especially they can't do running subtraction. It's difficult to do. However, a lot of people can do running addition quite easily. So in banking, there are no negative numbers. There are two sets of books, one that represents a positive increase in a bank balance and one that represents a negative displacement on a bank balance, but they're both added, right? So in other words, you add all the debits, you add all the credits, and they should balance to zero. So even banking is all addition. There is no subtraction, and there is no negative. They can show you a negative if there is a difference between the debits and credits, right? There are more debits from your perspective than there are credits, then you have a negative bank balance. I just answered your question. The reason that they're assigned and unsigned is because the CPU could not support negative numbers without it. Read about 2's complement. It will answer all your questions. No, it's not about resource allocation. That's not, no. I'm going to explain this again. This is very simple, okay? You have a CPU. CPU has a register. That register holds bits. Don't even think of it as a number. Don't think of it as decimal. Don't think of it as hex. Don't think of it as octal. That's going to confuse you. A register is a set of on and off switches. That's all it is, okay? Now, show me with 1 and 0 how, where's negative here? How do I make a negative out of 1s and 0s? How's that possible? It's not, right? Not directly. I can't put a negative in front of the bits. It doesn't work that way, right? But what I can do is I can say, okay, I have 1, 2, 3, 4, 5, 6, 7, 8. There's an 8-bit register. Okay, I'm a clever guy. What if I said that this very first bit, that's right. So what if I said this very first bit is a magical bit? It's a bit that means that it's negative. So then I have 7 bits left, right, that are the value, right? So for a signed number, you have 7 bits in an 8-bit register that can represent some value. This bit is whether or not it is signed, is whether or not it is negative. If this is 1, then it's negative. If this is 0, then it's not negative. However, why would you do that globally? Because if I do that globally, then I just reduce the number of bits I have. Now, 1 bit is fully dedicated to being a signed bit, and the other 7 bits are value bits. But I'm losing a lot of number range. And if I never need to deal with negative numbers, then that's a waste. I'm wasting a bit. So instead, what CPUs do is they say, hey, we're going to give you the best of both worlds. We're going to do this 2's complement thing, where if you set this bit up front, we're going to interpret that as negative. And then the rest of these are value bits. Now you're going to lose some range. No, it's not about resource allocation. It's about functionality. It's about the scheme itself, right? Well, I guess you could look at it that way, but that's not why there is signed or unsigned. Has nothing to do with whether or not you're going to waste memory or not. That's the only way you can represent negative numbers with the technology we have right now. Now, there are older CPUs that use binary coded decimal and use other things, right? Use other techniques, but those techniques have never really, they were very niche, right? Most CPU manufacturers never went down that road, with the exception of IBM and some other CPU Amdahl. Nobody else did it. So, anyway, that's why CPUs make a distinction between signed and unsigned, because you need some kind of scheme to identify negative numbers, because there are no negative numbers in binary, not inherently. Okay, quantum computing is... Quantum computing is not really the same thing. Quantum computing is based around qubits. A qubit is a superposition of 1 and 0. If you've studied quantum mechanics, then you know that superposition means that there is a probability number assigned to whether that particular qubit would be 1 or 0. Of course, if you collapse the wave equation, then it will become 1 or it will become 0 because you've observed it. However, if you leave the state isolated, if you leave the wave function intact and you leave the system, isolated from observation, which is a very difficult thing to do, then a qubit has some probability that the superposition is 1 or 0. Now, if you have 10 of those or 100 of those or whatever, now you have a whole bunch of qubits that have different probabilities of their, their superposition being 1 or 0. So assuming you can then program, right, such a machine, which would not look anything like what we do now, then you are essentially describing, I don't even know what you'd be describing, wave equation distribution. It's not anything like what we're doing today in computers, which is why it's still in its infancy. It's a prototype. No one's using these, with the exception of the NSA, probably. People who have infinite amounts of money and time and can put thousands and thousands of people on these to write the most simplistic programs for the most simplistic problems, because the idea of computing in the quantum space is we just don't have the tools for it, right? These are folks that are developing the tools. So it's even conjecture to really talk about what it is, because I don't even think they know, right? Do modern computers use first 1 as negative and 0 as positive, or 8 zeros as smallest number? No, the first bit is 1 in 2. Again, read about 2's complement. 2's complement will answer that question for you. There are multiple ways. There's 1's complement, there's 2's complement, there are others. What you need to know is what your CPU in question supports. If you look at the documentation, it will tell you. I'm going to almost guarantee that the MIPS CPU that you're using is 2's complement. However, if it's a different kind of complement, then you'll need to read the documentation to know what that is. What would be the benefit of quantum computing in theory? Again, computers today are machines that are like player pianos, okay? If you've ever seen a player piano, how does a player piano work? You feed in a tape or a piece of paper or something that has little notches in it, and there's a mechanism that reads, each instruction off the sheet and plays the appropriate keys. That's all computers are today. It's just that they can do that really, really, really fast, and that we've managed to shrink them down, so we've made them portable and less power hungry, and they have this concept of memory, right? So a player piano doesn't really have memory, but so the combination of a tape that has a bunch of little notches in it that tells the machine whenever it can match those notches, this is what it should do. And, oh, by the way, here's a little place where you can store temporary values and get them back. That's a computer today. It is an imperative, stepwise machine, meaning that you tell it start here and it goes through the tape until it either breaks, right? In other words, somebody put a bad instruction on the tape, or it reaches an endpoint. And that's all CPUs do today. So they're sequential by definition. So the idea, we have multi-threading, but that's an illusion. That's a bunch of tape feeders running in parallel, and then we've come up with ways, sort of, to share things between the tape feeders. But then that causes problems. So we don't really have parallel anything. The operating system I'm using right now, the operating system you're using right now, it's multitasking, but it's doing that by switching. It's doing that by using that memory bucket, taking stuff off the tape, putting it in that memory bucket, loading other state from the memory bucket, and resuming a different part of the tape. And it just does that very, very fast. And because it does that very fast, it appears as though your machine can do many things at once, when in reality it really can't. So, what's the limitation of that? Well, the limitation of that is no matter how clever we try to be in programming these tape feeders, we still are kind of stuck with the reality that they are tape feeders, that they have a needle, the program counter, and that needle runs over the tape. And it can do that really, really fast, but that's all it can do. And no matter how high level our languages are, no matter how many layers of abstraction we put on top of it for ourselves to make it appear to us that things are much more abstract and high level than they really are, the machine hasn't really changed all that much. It is what it is. So that means that there are a class of problem that are not, they're just not conducive, right, to that kind of a machine. No matter how fast it is, you can't cover the problem space quickly enough. So as an example, prime numbers. Let's talk about prime numbers. What's the fundamental underpinning of RSA security? The security that protects all of our financial transactions and our passwords and everything else in the modern era. It's the idea that if you take two really large prime numbers and you multiply them together, a tape feeder machine can't decompose those primes. It can't look at that big number and say, oh, well, that was obviously this really large number times that really. Can't factor them, right? Why can't it factor them? Well, it can. It's just that it has to do it as a tape feeder does it. It has to run the needle over the program and repeat, because it's by definition a sequential iterative machine. It does not have the ability to take that problem, split it into parallel spaces, and run those things simultaneously. Okay, so in theory, if, and again, I want to stress that, like, they're still trying to figure out how to practically take, right, something like a quantum computer and apply it to problems. But in theory, a quantum computer could factor very large numbers into their prime constituents because of the nature of the wave equation. So now, if you don't understand what the wave equation is, then you probably need to read about that, right? And quantum mechanics is super complicated, right? So it's just not something that you're going to understand off the top of your head. But in theory, it could solve those kinds of problems very well, because for all intents and purposes, a quantum computer with a sufficiently large number of qubits could represent that entire problem space parallel, truly parallel. But again, unless the NSA has some magic, then they're never going to tell anybody about. I think we're a long way away, like probably 20, 30 years from quantum computing being something that someone that does not have tens of millions of dollars at their disposal could make any reasonable use, even in the most simplistic cases. So that's the theory. I think we're a long way away from that being realized as a practical thing. Yeah, you can have multiple CPUs in a computer. We have that now. We have computers that have cores. Each core is, for all intents and purposes, a separate CPU. However, they are a separate CPU. They all run, their needle starts at a point in memory and it goes. It just reads. It just does its thing. And one of the challenges of multi-threading, right, is how to deal with, you have these separate things that are running independent from each other. How do you deal with changing state between them, right? It's a challenging problem. And I would argue that no one really has a great solution for that, right? There are ways you can use it, but it's not trivial, right? Huge and all, you're making this way too complicated, right? Correct. HACSTE said, depends, some CPUs instructions don't care, some have to interpret it, and that's, you didn't miss anything, Igloo Kid. Here's my sum up of quantum computing. It's nothing right now. 2030. Revisit the topic in 2030, see if somebody's done something with it. Between now and then, and I'm not saying by 2030 you're going to have anything. I'm just saying it might be slightly more interesting by 2030. Quantum computing, if you really dig into it, right? Don't just read headlines. Don't just read the Star Trek-like descriptions of shit. Like, really dig into it. How do they have to build these computers? How do they have to make these things work? They're using, superconductors and liquid cooling so they can get these things near zero. None of it's freaking practical, right? It's a long way off. It's a long way off, right? Decades. No, I'm just saying people ask about this stuff, it's sci-fi, right? Like, literally, it's not, if you look at the reality of it, there are some potential use cases for it. Those use cases, I guarantee you, will not impact, you can't do anything with any of those use cases. And again, the practicality of it is that it's decades away, right? It is decades away from even being something that people who have hundreds of millions of dollars that they could burn every year would be able to even consider using it, right? It's just not something that any of us are ever gonna probably have to deal with. In quantum computers, unless there's something that I'm missing, you're never going to play your next great video game on a quantum computer. Most likely not. Now, I know that a lot of scientists, a lot of physicists want to simulate things with quantum computers, but again, that's what they would like to do. Where we're at today and how you would even do that is like, nobody, I think if you talk to anybody in the field and you ask them point blank questions, they can't tell you how we're going to get from where we are now to there. We're not there yet, right? We don't really know how to program a quantum system to even begin to approach the complexity of a game or anything like that, right? Maybe maybe a quantum machine would be very good at doing it, but we first have to figure out how we would do that, right? And we're not there yet. I mean, just look at the computers we have now, and yeah, on the one hand, you could say things have evolved really, really quickly, but on the other hand, we're still kind of arguing about how even to develop the software that we develop now. And something on a quantum computer, yeah, I mean, we haven't even gotten to the point where we're going to argue over the equivalent of goto in quantum computing yet. So, yeah. The holodeck, I think, has a long way to go. I have no idea. Look, first off, I think it's an invalid question from this perspective. All audio processing is an illusion from the perspective that, like, stereo, okay, that's 2 channels, that's real, but like all the other stuff they do, that's just that's like clever shifting of sounds through audio channels and things. So fundamentally, you're listening to something that your 2 ears can hear. It's relying on the fact that your brain takes timing cues from audio to reproduce spatiality, right? So they've figured out over the years, well, if we put this sound on this side of this channel and then we emulate a Doppler shift in this way when it's encoded, when they hear it back, their brain's going to interpret it as if it's moving in 3-dimensional space, because how does your brain know any different, right? It doesn't. It's hearing the sound the way that it would hear it as if it were hearing it in the real world. So it's a simulation. It's an illusion, right? All that stuff is illusion. Just like looking at a 3D image on a screen is an illusion, but it tricks your brain. And no one's arguing that a monitor has depth to it. It doesn't. But it can seem as though it does, because that's what our brains are trained, are built to interpret. They're built to interpret a stereoscopic 2D environment and turn that into depth cues internally that have, like, you truly feel like you're perceiving depth, but there's no depth there. And that's the other thing too. We don't see in 3D what is 3D. We don't even know. We have 2D inputs to our brain, and our brain is extremely advanced and is able to take those 2D inputs and derive depth cues from it. Just like our ears are able to deal with time shifting of sound input, and that time shifting becomes cues the brain is able to interpret, that it turns into spatial information. Or I should say our perception is that it's spatial, right? Yeah, I don't know anything about the qualitative aspects of it. I know people, I have friends who swear by the latest and greatest audio everything, 7.1, all that stuff. I notice small audio cues. Again, a lot of it has to do with whatever it is you're consuming, right? If they actually put the effort into encoding things in such a way that it takes advantage of the format. But again, like stereo headphones theoretically could do everything, right? If things were, encoded properly, then you could get the same effect from a stereo headphone. Now, there might be real challenges in terms of like why encoding that for pure stereo headphones is not, in practicality, it's not, you're not going to get the same results because of some other reason, right? But theoretically, you do only have two ears. You should be able to deliver an audio signal timing just right to both ears to emulate any kind of aural space that you want. But again, there might be practical limitations on the encoding side that make that not pragmatic. I kind of personally think things like 7.1 and 5.1 and all that stuff were just ways for the audio industry to sell people more speakers. But, all right. I'm going to have to wrap this up. So where did we get to? So on transmute, I added type location because we need to cache the type location information at conversion time. In the emit for transmute, we infer the type for our expression, the thing that's inside of the transmute operator, parentheses. If the source type is none, if the number class of the source type is none, then that's an error, right? We can't transmute from anything but a numeric type right now. And if the target type is not a number, that's also an error. And that was pretty much it for transmute. Was just adding the air conditions. I tested some of the air checking on cast. We're going to look at that here in a sec. So on cast, we capture the type location. It's almost exactly the same as transmute. So then I started actually working on the implementation of cast, and I've got my rules kind of written down here. We've got our air conditions, and I added the code to kind of pick the right mode of what we're going to do. But I need to think about, for like zero extend and sign extend, I have to think about how I want to do that. What I was originally thinking is I would just add some extra instructions that would handle doing the zero extend and the signed extend. But I need to refactor the register for and the assembler variables to kind of be able to either inject sign state or break up how things are being ordered in the output. So I got to figure that out. But structurally, I think I have all the parts to finish cast. One thing I think I probably will do is move some of these local variables up so I'm not doing duplicate work up here. And then an AST evaluator for the cast expression, we capture the type location on the element so we can use that for error reporting. Same thing with transmute, we capture the location. In program, there were a couple bugs here around categorizing global identifiers. So I fixed the logical flow here, and I took out the extra condition I had on this. I don't even know why I had that condition there, but I fixed that issue. So that's working properly now. Yeah, so incremental progress. I got to noodle on how I'm going to do that. Handle the sequencing really is what it comes down to, because register 4 calls read on the variable, which is, so then that's happening out of sequence, and I really want to be able to control the sequence. So, yeah, I just need to figure out that. Once I figure that out, then I think the rest of these would be fairly straightforward. So I'm going to go ahead and check this in. So number 20. Okay, that's going to do it for me today. Hackintosh. I'm going to say the same thing I say every time about that stuff. It's the same thing I say about Linux. You have two resources, okay? One is time, one is money. Oftentimes, people who have one don't have much of the other. Sometimes people have both, but it's rare. Typically, you'll either have lots of time and no money, or you'll have lots of money and no time, or you'll have, slightly more money than time. One of those resources is more precious to you specifically, than it is to anybody else, right? You're going to meet a lot of people who they value their time more than they worry about money, right? So say a Macintosh costs $1,000 US. I do too. I value my time a lot. So I'll say what I always say about this stuff. If you have the time to dick around with a Hackintosh, good, great, go for it. If you can get it to work and you can deal with Apple continuously trying to shut you down, then that's fantastic. You saved yourself $1,000 US or whatever. However, if you track the amount of time you put into it, I think you'll discover that you're losing money, right? But that's okay. Some people, I'm not saying it's legal, and I'm not saying that I approve. I'm saying that if you value money more than time, or for whatever other reason you would not wish to purchase things from Apple for ethical reasons or whatever, then again, that's your call, not mine. And if you have the time to sink into a Hackintosh, then by all means do so, right? But it's a waste of time for me. And so I don't put much thought into it beyond that. Which incidentally is the reason I don't use Linux as my primary desktop operating system. I don't have the time. So, okay, let's see if we find somebody to host or raid. Let's see. We did Brooke Zerker yesterday. This one, it says French and English. I don't know which. I'm assuming she's primarily speaking French. Synox would be good. Can't really tell. She's okay? All right, I'll rate her. I haven't rated her yet. All right, trade. All right. In Hai, we are rating her. So say hi, be nice. I'll be back online Monday at 5 a.m. And we will continue wherever I leave off. So have a good weekend, everybody. And I will talk with you on Monday. I think I probably will make some good progress this weekend. I'm hoping. Talk to you then. Bye.